If you frequent any sort of scientific news website, then you may have heard about something called quantum computing, or computing using quantum mechanical properties. But most of the descriptions from these websites probably differ or even contradict one another. This confusion is not without cause. Quantum computing and even quantum mechanics in general is a very abstract and counterintuitive subject. This video will try to serve as a guide to quantum computing. But first, before we can talk about how quantum computers work, we need to know how regular computers work. Regular computers use bits, which stands for binary digit. A binary digit is anything that has two separate identifiable states, usually signified as 1 and 0. A coin is a great example of a bit. Heads can refer to the bit being 1, and tails can refer to the bit being 0. Computers that use bits are known as classical computers. Quantum computers, on the other hand, use qubits, which stands for quantum binary digit. A qubit can be any two-state quantum mechanical system, which is jargon for any system that has two independent states, again represented by 1 and 0, and also experiences quantum mechanical properties. An example of a qubit is the spin of an electron, which can be either spin up or spin down. However, for our examples, we will be using a theoretical quantum coin as a qubit, where heads is state 1 and tails is state 0. Remember how I said qubits differ from bits because they experience quantum mechanical properties? Well, unlike how bits can only be 1 or 0, qubits can exist in a superposition of 1 and 0. Superpositions can be described as a quantum coin that is continuously flipping. You do not know whether it is heads or tails until you measure it, stopping the coin from flipping and collapsing the superposition. If you know of the famous Schrodinger's cat thought experiment, the cat in this case exists as a superposition of both dead and alive. Only upon opening the box does the cat superposition collapse into either a dead cat or an alive cat. It is important to note that until you stop the quantum coin from spinning and measure it, the quantum coin has no definable state. But the probability of a quantum coin in a superposition being heads or tails isn't always 50-50. That is to say, the quantum coin isn't always fair. You can think of the probability of a quantum coin being represented by a point on a globe, the scientific name of which is known as a Bloch sphere. The latitude of the point refers to the probability of the quantum coin being heads or tails, with tails being at the North Pole and heads being at the South Pole. The equator on this globe represents a 50-50 chance of the quantum coin being heads or tails, with latitudes closer to the North Pole having a higher chance to be tails, and latitudes closer to the South Pole having a higher chance to be heads. Note that all points on the same line of latitude have the same probability, as quantum coins can be distinguished from each other even if their probabilities are the same. But superposition isn't the only quantum mechanical property used by quantum computers. Imagine a scenario where a pizza is ordered and half of it is pepperoni and the other half is just cheese. This pizza is split in half along the middle so that each half contains only pepperoni or only cheese. Each half is then either given to Alice or Bob. Upon looking at the pizza half they got, Alice and Bob can deduce what half the other got. If Alice got cheese, she knows that Bob got pepperoni and vice versa. But what if this happens with a pizza that is not in a defined state? What if Alice and Bob were instead given one half of a quantum pizza that was neither pepperoni nor cheese, instead existing as a superposition of both? If Alice measured her half of the pizza and it ended up being pepperoni, then she knows Bob got the half with only cheese, even if Bob had not measured his half. This would suggest that somehow Alice's half of the pizza influenced Bob's half. Even if Alice and Bob are light years away from each other, and they both measure their halves at the same time, the results would still match up, suggesting that the pizza halves communicated with each other faster than light, as if to decide which half should be pepperoni and which half should be cheese. This is known as quantum entanglement, and is very important to quantum computing. But the entangled qubits aren't limited to opposites. If the quantum pizza was instead either all cheese or all pepperoni, then Alice would know that Bob's pizza half has the same toppings as hers. It's important to note that no information is actually transferred through entanglement, nor do the pizza halves have hidden information in them that predetermines their toppings before measurement. Unfortunately, these proofs are too big to fit into this video, but I encourage you to research them yourself if you are interested. Quantum computing uses qubits, superpositions, entanglement, and many other properties to actually compute things. A very vague description of how they work is by taking many different qubits as an input, either converting them into superpositions or using existing superpositions, creating large entangled states with the qubits, and using interference to simplify the entangled qubits to output an answer. Most of the algorithms used in quantum computing are probabilistic, meaning that the correct answer only has a high chance of being measured. This requires multiple measurements to find the correct answer. Some algorithms, however, are deterministic, meaning they always give a clear-cut answer. The main use of quantum computers is not breaking through modern encryption, unlike what popular media suggests. No, the most important use of quantum computers is simulating quantum systems, something that is basically impossible for a classical computer to do on a large scale. This is due to n amount of qubits requiring 2 to the power of n classical bits to be simulated. This should also be stressed that quantum computers will not be any faster than classical computers in most situations. Quantum computers are getting better and better every year and are definitely going to make a big impact on the world.